So in this section, we want to talk about the concept of isotopes. So atoms that have identical atomic numbers, so the Z number, the number of protons, if they are the same, but they have different mass numbers, or A's, these are called isotopes of the same element. So protium, deuterium, and tritium are three isotopes of the element hydrogen. So the protium, listed as H down here, is the most abundant hydrogen isotope. It has one proton and no neutrons. And so that is kind of our definition for hydrogen. If we look at our periodic table, so if we just jump back here really quick, we'll see that hydrogen has an atomic number of 1, and then the atomic mass is very, very close to 1 as well. So we would round this to 1. If you subtract 1 off, you would see that there are 0 neutrons in this atom. However, you can see that the atomic mass is not quite 1. It's 1.00794. And so the other isotopes of hydrogen are accounting for the weight change. So it is divergent from 1 because of the presence of the other isotopes. So the deuterium isotope of hydrogen is heavier than the protium. It has a Z number of 1, so it still has 1 proton. So again, the number of protons are the defining feature of an element. All elements that have 1 proton are going to be hydrogen. The atomic mass for deuterium is more than the protium. So the atomic mass is 2 in the case of deuterium, suggesting that you have 1 proton and 1 neutron that's going to be present here. And for tritium, it's got 1 proton again, so the Z number stays the same, but the atomic mass is going to be different. The A number is now 3, which suggests that there are 2 neutrons and 1 proton based on the Z number, or the atomic number. So again, the defining feature of an element, these all have the same physical and the same chemical properties because they have the same number of protons that are present, which means they also have the same number of electrons in their elemental form. Each one is going to have 1 electron that's associated with it as well. The only thing that differs is the atomic mass, or the number or amount of neutrons. And so there's different abundance of different isotopes on the Earth. So in the case of hydrogen, the most abundant form of hydrogen is the protium form that only has 1 proton and no neutrons. So this is the most abundant form, and so the mass that's presented on the periodic table represents the most abundant form. And so it's going to be a combination of all 3 of these different isotopes, but it's based on the percent of the compound that's present on the Earth to help make up that overall or total weight. So this is just showing the 3 different forms of hydrogen. The protium has 1 proton and no neutrons. The mass number is 1, and the atomic number is also 1. You can see that the atomic number stays the same in the other isotopes. The atomic number is always 1. There's always 1 proton. But in the case of deuterium, there's also 1 neutron in here, so the mass number increases to 2. And in the case of tritium, there's 2 neutrons and 1 proton, and so the mass number becomes 3. So you can see if you have solid water made with the protium, the most common form, then the ice cubes are going to float in the liquid water, and they will be less dense and they are less heavy. But as you increase the mass, if you make ice cubes out of deuteriated water, so it's got deuterium as the major form of hydrogen in here, you can see that the mass actually gets heavier, and now the ice cubes are going to sink. So this is called heavy water. We can use deuterium and we can isolate it and we can utilize it in experiments to try to figure out different features of enzymatic reactions or other molecular structures that can help us determine other components within a cell or within a system that we want to study. And so it's a useful tool that we can use. However, we're going to note that all of the other physical and chemical properties of the deuterium outside of this mass change are going to be the same as the protium. So they're going to be able to do the same kinds of reactions. They're going to have the same chemical reactivity. They're going to have the same physical properties except for the mass. So the density will change a little bit. Anything that has to use the mass to determine that physical property is going to change just a little bit. And that's the only way that we can tell these apart. All of the other fundamental units, the melting point, the boiling point, all of these other physical properties are going to be the same within these different isotopes. So when you have different isotopes of an element, they can be represented by having the symbol of the element and then using subscripts on this side of the atom. So this is not the way they're represented in the periodic table. Remember, in the periodic table, we only get the atomic number and the mass number. But when we're actually writing these down, if it's not the most common form of the element, if it's a different isotope, we need to indicate what isotope it is. And so for this, the mass number is going to be a superscript in front of the elemental symbol, and the atomic number will be the subscript. So you will see isotopes written in this format. So this would be representative of tritium. Tritium is also a radioactive element. And so it's inherently unstable, and over time it actually will decay, and there will be fragments that come off of that nucleus, and you will lose some of that mass out of the tritium element. And when you lose mass, if you have neutrons shoot off of a molecule, or if you have protons come off, or if you have electrons come off, these are very reactive components because anything charged is very damaging to other forms of matter. They're very reactive particles that can bust apart and try to neutralize themselves. So things that are charged are very reactive, and so we will talk a lot about charged particles, electrons and the protons, as we start looking at chemical bonding and chemical reactivity. And so that's why radioactive elements are very damaging to biological systems, because they release charged particles, and these charged particles then are very reactive until they can become neutralized. So overall, a summary of our isotopes. Isotopes of the same element have the same number of protons. Their atomic number is going to remain the same. They have the same number of electrons then, because they're going to balance out the same number of protons. They have different numbers of neutrons, so their atomic mass is going to differ from one another. So the chemical behavior then is largely determined by its electronic structure or the structure of the charged particles. So different isotopes of the same element exhibit nearly identical chemical behavior because they have the same number of charged particles present. The only thing that differs is the number of neutrons, and that doesn't change the behavior of that element. So Niels Bohr was the one that realized this link between the isotopes, that they're fundamentally the same element. And so what he did is he restructured the periodic table that Mendeleev came up with based on this information, and he arranged all of the elements in the periodic table based on their atomic numbers rather than their atomic masses like Mendeleev did. And so all of the isotopes for a single element are included as a single entry on the periodic table. They're not included as distinct entries. So all of the different isotopes of carbon are represented by this one symbol on the periodic table. All of the isotopes of carbon have an atomic number of 6. They contain 6 protons, so this is the Z number. The elemental symbol is present, and then the atomic masses that are present on the periodic table are representative of all of the different isotopes that are housed within this entry. And they're based on abundance. And so we'll take a look and see how this is actually measured. So carbon has 6 protons and 6 neutrons. So the major isotope of carbon has 6 protons and 6 neutrons. So it should have an exact atomic mass weight of 12 atomic mass units. So the mass units on the periodic table represent relative masses, an average then of the percentage of each different isotope that exists on the Earth. So carbon is a great example of an element that has a lot of different isotopes. There's 15 known isotopes for carbon. They range from C8 to C22. And so these are the atomic mass numbers. So all of the carbon isotopes, they all have 6 protons. So they're only going to differ in the number of neutrons that they have. So a C8 is only going to have 2 neutrons and 6 protons. C22 is going to have 6 protons and 16 neutrons to get up to a mass of 22. So 2 of the elemental forms of carbon are the most stable. C12 and C13 are the most stable isotopes of carbon. So the others are pretty unstable isotopes, and they will decay into different elements over time. So when they do this, when they decay, they're going to release energy that is often harmful to us. And so these are termed the radioactive elements. So radioactive elements are unstable elements that are going to decay over time into other elements. And to do that, they actually have to lose protons to become different elements. And if they're going to lose those protons, they also have to lose electrons. And so when they do this, when they decay into a different elemental form, they release this energy, and that energy is very reactive and harmful to other matter that would be near them. If that matter happens to be you or another person, it can be very damaging to your matter that makes up and constitutes your body. So one of the radioactive forms of carbon that is found most often on the Earth is C14. It's the longest lived radioactive form of carbon and has a half-life of about 40,000 years. So you can see that radioactive elements don't necessarily decay very quickly, but over a period of 40,000 years, half of the C14 that would be present within a substance is going to decay. And so there is some proportion of C14 inside all living organisms because there is a small abundance of C14 on the planet. And remember, these different isotopes, they have all the same chemical and physical properties that the other forms of carbon have. So our body doesn't recognize C14 any differently than the C12, and it will incorporate it into the protein structures, the DNA structures, the lipid structures within our body, and will utilize the C14 just like it's C12. So every organic substance, so anything organic contains carbon in it, is going to have some relative abundance of C12. It's going to be mostly C12 because that's the most dominant form of carbon on the planet. And then it will have some C13, and it will also have some C14 isotopes. So there will be some small fraction of carbon within any living organism that has C14. When that organism dies, there will be this decay process over time, and some of that carbon 14 is going to be lost because it's changing into a different elemental form relative to the carbon 12 that would be present within a sample. And so we can measure relative abundance in fossils that we find or bones that we would find, and we can use carbon dating back to about 40,000 years to determine the relative age or when that fossil was created or when that organism actually died. So the atomic mass that's represented on the periodic table is actually the weighted average mass of an element's atoms in very large samples. And so this includes all of the naturally occurring isotopes of that atom. So when you want to calculate the atomic mass of the element, you have to know the individual mass of each isotope, And you have to know the percent abundance of each isotope to be able to calculate this. So the atomic mass is represented then by a summation. And so it's a summation of the isotope abundance times the isotope mass, and then you sum all of these different isotope abundances until you get 100% of that element represented on the periodic table. So this Greek symbol here, this represents a summation. And so let's do a summation. So we can say that C12 and C13 make up most of the carbon on the planet. And so we'll use these just to calculate the relative abundance. But you can see it gets much more complex than that because there's 15 different isotopes of carbon, and they're actually utilized to represent the mass weight that's represented on the periodic table. But we can get very close just looking at carbon 12 and carbon 13. So when we have carbon 12, we know that 98.89% of the carbon on the planet is going to be represented by carbon 12. So this is the natural abundance that occurs on the Earth. So 98.89% or 98.89 over 100, that's represented here. So the ratio is actually represented in the equation. So isotope abundance is going to be 98.89 over 100, which gives us 0.9889 in our equation. C13 makes up only 1.11% over, so this is 1.11 over 100. So that would give us 0.0111 in our equation times the atomic mass of 13. And then you sum these together, so you would add these together. You would go through, if we were to calculate the actual mass weight of carbon, you would do this for the other 13 isotopes that were present, and you would add them into the equation as well. So we can see that the proportion of carbon mass that's attributed to the carbon that's on the Earth from carbon 12 is 11.8668. And we can see that only 0.1443 of the carbon 13 mass is attributable to the overall carbon weight on the planet. And so when we look at the periodic table, this atomic weight or atomic mass is representative of the most abundant isotope that's on the Earth. So for carbon, 98.89% of the carbon on the Earth is carbon 12. And so the atomic mass reflects this. It's very, very close to 12. Even though there's 15 different isotopes on the planet, and the one with the highest mass is 22, you can see it doesn't really affect the overall atomic mass of carbon on the planet very much because it's in such low abundance and it's so unstable. So let's get a little bit more practice and try one more problem for our isotopes. So copper exists in a couple of different major isotopes. And so the first one is copper 65 and copper 63. And so the atomic mass of each of these is 62.93 atomic mass units. And the abundance of this is 69% essentially. And then there's 64.93 atomic mass units for copper 65. And so if we go through our equation and do the summation, we're going to take the atomic mass units times the percent over 100. So 30.83 over 100 would be 0.3083. We would put that into our equations. So if we're doing the copper 63 first, we can see that 69 over 100, 0.6917, this is our percentage or our natural abundance, times the atomic mass units. So this is the representative weight that's attributable to copper by this specific isotope. We do that for copper 65 as well. 30.83% of the copper is in this form. The atomic mass unit is here. And so the weight that's attributable from this isotope is 20.02 atomic mass units. We have to then add these together to get the atomic mass of copper, which is 63.55 atomic mass units. So we can compare this with the number on the periodic table, which is 63.55. So we can confirm that here. Copper here, 63.546, very close to 63.55 if we've rounded up. So the major isotopes of copper then are going to be copper 63, major isotope, and then the second most abundant is copper 65. And these ones contribute most to the molecular weight.